What's up, guys? Welcome back to another episode of the Modern Goonies podcast. I'm your host, Trevor King Minor, and I'm hanging out with my lovely co-host, Michael Ross.
It's your boy, Michael Ross. Again, what's up?
I think the first time you said Michael fucking Ross.
Oh, is that what I said?
Yeah,
okay.
There we go. We got to start.
It's your boy, Michael fucking Ross.
There we go. All right, guys, so welcome back. This is Season 1, Episode 2 in our 10-episode season. And the topic tonight is going to be the beginning and the end of the universe. So, yeah, I got to tell you, man, and you already kind of know this, I went down a fucking rabbit hole at work just researching this for at the end of last week and the beginning of this week. And I fell like completely headfirst into it on Monday, just trying to wrap my head around a lot of these concepts. So, like, I had always had like a base idea of the Big Bang and, you know, how it kind of came about. But then depending on the videos that you watch or like the things that you read, they just get so detailed that, I mean, honestly, I couldn't even wrap my head around some of it. But then it's like, then you start understanding some of it and you're like, there's no fucking way I can tell this to somebody else and they would understand what I'm talking about.
Yeah.
So, yeah, it's like a fine line.
Well, you would sort of expect that with something as vast as our universe. Like, something as complex as that more than likely doesn't have a very simple beginning.
No, yeah.
Not too simple.
Well, yeah, well, it's funny because a lot of people, when they think of the Big Bang, they think of it in simple terms of nothing, explosion, things, and it's like that is just not how it went. So, the way I wanted to do this one is, you know, I wanted to talk about the beginning and the end of the universe, what we know for a fact happens at the beginning, and you know, some of the things that we don't know about it, and we can kind of go through some theories or cool ideas of maybe what happened at the true time zero beginning. And since we're doing that, it's like we might as well, because some of the math kind of works out in such a way that the end can also cause the beginning. And I thought that was really dope. So you can't really talk about one without talking about the other. And so that was something else. Like while I was going through this, I felt like I was in an episode of Dark, like the end is the beginning, which is also the end. Like fucking.
Yeah, I felt the same. Like I was writing my notes on the beginning and like the end popped up. I was like, okay, I'm still going to put beginning and end sections here, but you know.
Yeah, I honestly didn't know at first which one, like, do we start with the beginning? Do we start with the end? So I think the most important thing is we should talk about the beginning and what we actually know about the beginning, and then we can start talking about the end. So, you know, I've got some notes here. So we'll start with the Big Bang, and we'll start with everything we know about the Big Bang. So one of the things that I came to realize, and this was something I hadn't actually considered before, but the Big Bang is actually kind of like a misnomer in a way, because a lot of people just kind of describe it in terms, like I said a minute ago, just like explosion, and then everything is in existence. And what I've read is that it's probably more accurately described as like the big expansion.
Yeah.
That everything. So when people are referring to the Big Bang, what they're actually talking about is basically the time of expansion from the universe from subatomic until like what it is today. Yeah, subatomic to cosmic size, I guess how they frame it. I guess we should maybe go into like how we kind of figured out about the Big Bang. So what do you know? I mean, studying physics, I'm sure you obviously know like how we kind of discovered this, but what is it? What have you read or what have you kind of looked into?
So have you heard of Edwin Hubble?
Mm-hmm.
Okay. The man that the Hubble Space Telescope is named after.
Yeah.
So Edwin Hubble and an associate of his, I believe her name was Cecilia Payne Gaposchkin.
Jesus. Props to you.
Thank you. So she discovered something important about, I think, how fast the universe is expanding, but Hubble discovered that the universe was expanding.
Yes. Yeah, so Hubble looked into the night sky. So a lot of this, the first person to kind of come up with an idea that the universe is expanding or it might have had an origin was Einstein, because, you know, he did the theory of general relativity. Mm-hmm. And a lot of what his math was going for, it worked out more in the sense if there was like an expanding universe, but he assumed, like most people did, that the universe was just static. And I think we kind of ran with that until Hubble, you know, made the telescope and he looked out and he noticed like, oh, what the fuck? I think he mapped it through like infrared or some shit like that. And he noticed that the galaxies were moving like, away from each other. So so automatically an idea that Einstein was kind of like, it kind of makes sense if it's like expanding, but whatever. And then it's like years later, I think it was like a couple decades later, it's like, hey, it is expanding.
Yeah. So Hubble was the man who discovered that
Yes.
the universe was expanding. And not just expanding, but expanding faster the farther you go.
Yes.
And the next logical step from, hey, the universe is expanding, is what did it expand from?
Right.
So, admittedly, I'm not well versed in the history of this, but after Hubble's discovery that the universe was expanding, like the next step was to figure out what it expanded from, and the natural conclusion is if the universe is effectively spherical, or if the observable universe is effectively spherical, then the universe came from a single point.
Yeah.
And that's the Big Bang.
Yeah, pretty much. So then, somewhere along the line, they kind of coined the term Big Bang because they noticed, well, hey, if it's expanding, then there must have been a point where it was smaller because things would have been closer together.
Exactly.
So then time moves on, and basically, I don't think I wrote down the names of these dudes, but so it says here. So scientists concluded that due to the abundance of heavy elements in the known universe, that the universe at one point in time was probably a lot hotter and denser, which would have made sense because the more it contracts, the hotter it gets. So that was one of their theories that they went on. That they kind of like had an idea about, like we don't really know if that's true. But then in about the 60s, these two dudes were working on a satellite that measured microwaves.
Yes.
And this is super important.
Yeah,
that measured microwaves, and they found microwaves coming in all directions, and they thought that their satellite was fucked up, and they're like, well, this can't be right, but it was right every time. And they had accidentally discovered what's known as the cosmic background radiation. And because of discovering the background radiation, this was actually the point in time where most scientists started to agree that the Big Bang was the most likely origin of the universe. Because I guess it worked really well with like Einstein's math or something. Well, I took a lot of information from like PBS Spacetime and Kurzgesagt. They're amazing in explaining all this shit, and they kind of broke it down a bit. So PBS Spacetime kind of describes it like this, and they actually did a good job of like for fucking morons like me. Oh yeah, by the way, I forgot to mention this, but Michael basically has a master's degree in physics, so I'm like the moron just kind of trying to explain this shit to other morons, and he's the guy that like actually fundamentally understands a lot of it. So
humility is important.
Humility is important, but I don't have to give you humility. That's just for yourself. Okay, so let's go into, so a lot of people still to this day are kind of like skeptical of the Big Bang, which I always thought was funny, especially because a lot of this kind of comes from more religious sects. And when the Big Bang was actually first proposed, a lot of people considered it a theological answer because it's, there's a single point where everything just started happening, and that worked really well with religion. So people are still skeptical about it. So I wanted to kind of talk about why it is correct, or why it's considered correct, and some of the reasons why. So a lot of the math that we use to determine that the Big Bang was a thing is Einstein's theory of relativity, but also our basic understanding of the laws of physics. So here's what we do know. We know the universe is expanding. We can literally see it. And since we know that fact, we can use our knowledge of physics to run its laws backwards and kind of figure out what the universe would have looked like a long time ago. Well, the more you move it backwards, if it's expanding, that means at one point it was closer together. So the more you keep, the further back you go, the smaller the universe is. I mean, that's just kind of makes sense. You keep running it back, and it basically tells you that the universe would have been packed into an incredibly small point, which I guess is considered singularity. Is that right? Okay. So the way that we understand Einstein's math and our laws of physics, everything works all the way up until about 10 to the negative 32 seconds of the Big Bang happening. So like 10 to the negative 32 of, I think, 1 second or something like that. Like after the Big Bang, like our math works pretty well right up until that.
So from what I understand, before 10 to the minus 11 seconds, there's like nothing, sorry, I can't say nothing. But everything after 10 to the minus 11 seconds, we can support with lab experiments and like data that we can produce. Before 10 to the minus 11 seconds, but not before 10 to the minus either 43. I think it's 10 to the minus 43.
I think, yeah, that's it.
So
That's
10 to the
it.
minus 43 seconds is something called Planck time, which is the
Yes.
smallest measurable unit of time. It's got to do with fundamental constants of the universe that aren't going to matter to anybody.
Yeah.
But it's the smallest measurable unit of time because of how the constants are used.
Right.
Before that, things are irrelevant.
Things...
Not irrelevant, but unknown.
Yeah, so we threw a lot of random fucking big numbers out there, or I guess at this point, really small numbers, technically.
Tiny
Don't
numbers.
get caught up on that. So basically, all you need to know is that our math for why we think the Big Bang is a thing is because it works perfectly well. We can basically describe the conditions of the universe all the way up until literally a fraction of a second after the Big Bang. But because of that, like, so when you get to that point, and anything before it, like everything, like physics is basically just like fucked. Everything gets like super wonky. A lot of shit doesn't really make sense. Yeah. So the more you keep going back, and I keep reading this number about like 400,000 years after like the initial expansion. So basically, we don't really, so in that singularity, or I guess what would be considered time equals zero, where like literally time is created. Well, Big Bang Theory actually doesn't describe that at all. We don't have an answer for that. We have no idea what happened at the literal beginning of time. We just have the information of everything that happened a fraction of a second after that moment.
Yeah.
So before that moment, who knows? There's literally infinite possibilities on what the fuck happened in the singularity when time was created. So, score one for theologians because, God's not thrown out the window. We literally cannot describe what happens at the beginning of time, just everything after it. So I guess that kind of, in my eyes, doesn't really go well with there was nothing and then all of a sudden there's something, because that's not really how it's described.
Yeah.
So that's not even technically an accurate depiction.
See, a fundamental question, that raises something that I have actually struggled with for several years, like since I was, maybe in third grade. The question is, if the universe is there, then it has to be in something. You know what I'm saying? Like, I have a can of beer in my hand, but this can of beer is in space.
Yeah, it's in this room.
Yeah. So if the universe is there, wherever it is, what is the where?
Yeah, well, I guess technically the way that we look at it would be just literally nothing, right?
Like the way... So the answer that I have accepted, the answer that I force myself to accept, is that there doesn't have to be a where, because the universe is everything.
Yeah.
So, I mean, it's kind of a shitty answer, admittedly.
Well, that's the thing.
There is no where. It doesn't matter.
Well, there is no good answer to that, yet, like, nonetheless, because even if there is no where, we as humans can't really wrap our head around it very well. The idea that there's nothing. The best analogy I've seen of it is kind of like imagine you're standing, like an ant is on a balloon, and you just keep blowing the balloon up. Like, that's kind of what it's like to be inside of the universe. Like, but my issue with that answer is like, well, that balloon is still in the room that you're blowing it up in.
Exactly.
So it's always like a paradox, and I think existence in general is kind of just a paradox. So yeah, there's a lot of, I wrote down like a lot of shit that just, I think it would just be way too much to throw at people. But basically at about like 400,000 years after the Big Bang, there were still no stars, there was no anything, everything was just kind of in like this hot, dense, I guess kind of like a gas or a fog or something like that. And then at a certain point, hydrogen is created, and then basically light can finally everything can finally escape the small, hot, dense cloud, and then everything just starts expanding from there. And then that's when stars are formed, and that's when the universe kind of as we know it began. And that 400,000 seems to be like a pretty big marker because that's where, because of that, we know that that's when kind of like light was released and everything really started expanding, was because that is the moment that the cosmic background radiation kicked in. That is where we can read it all the way back to. So the way that we look at the cosmic background radiation is that it is the same temperature like all the way throughout if you're mapping the temperature of it, and that can pretty much only happen at that 400,000 year mark. And but that also that kind of goes into some of the issues with the Big Bang. Is kind of like right around this moment. There are some issues with the Big Bang that we can kind of like come up with answers to. So like our physics doesn't just get thrown out the window, and nonetheless like our physics works pretty fucking far back. So like our equations aren't wrong. It's just like there's a couple things that don't necessarily work, so you don't throw out the whole book. Like it's like, all right, we just got to kind of like figure out a way to mend that. Basically, when the universe was younger than 400,000 years, it was too hot for atoms to exist. And
that is a technically correct statement.
Okay. What is... Go ahead, Mr. Physics.
On the order of minutes, nuclei could exist, like protons and neutrons.
Yes.
And I think by saying atoms wouldn't exist or atoms couldn't exist, while correct, I think that would cause an audience to be misled.
Okay, that's fair.
So atoms are protons and neutrons and electrons. So before the 400,000 year mark, protons and neutrons existed, and they combined and created an isotope of hydrogen.
Okay.
But the hydrogen atom itself was created roughly at 400,000 years, when when the universe was finally at a low enough temperature
yes.
for electrons to combine or orbit nuclei to form atoms.
So that is in a little bit more detail than what I've seen, but that's obviously correct to the physicist here. So that is actually where, so you just said like at 400,000 years, like that, like the universe was finally cool enough to allow, basic particles to form. That's actually one of the issues with the Big Bang, is that we know that it took till about 400,000 years for the universe to cool that much to allow things to exist. Well, the amount of time, I guess, for the universe to cool that amount, it would not have had enough time in 400,000 years from the initial expansion to 400,000 years. Like that math doesn't add up. So what we had to do, and this is one, like a theory that goes into like the end of the universe and everything too, but like the inflation period, where basically at the 10 to the negative 32, that number I keep mentioning, that like physics still works, the universe is about the size of a grain of sand. So the only way for the universe to cool enough to allow matter would be if the universe started subatomic and then suddenly and inexplicably just grew to the size of what is it, like a fucking, maybe a grain of sand or football, but basically like it's subatomic and then it just immediately fucking inflates to a much bigger size. And that's really the only way it can allow for it to cool by 400,000 years. So where we see in the cosmic background radiation that everything is the same temperature. So do you know much about inflation? Because I don't.
No, I don't know very much about inflation. Cosmology is not something that we touched on very much in the classes that I've taken.
Okay.
Like we've touched on the Big Bang. We've touched on like the things behind it, but that's the extent of my knowledge without the research that I've done for this very podcast.
I see. So, once again, we keep throwing all this stuff out here of like, oh, well, this happened and then this happened. And one of the questions that I always had growing up is like, well, how the fuck do we know that? Like, this is so long ago. This is so much in my head, like crazy, this has to happen and this has to happen. So it must have happened like this. Like, how the fuck do you even know that? Like, how can you even come to that conclusion? Well, what I didn't actually know is that we've simulated a lot of these very conditions in our particle accelerators here. The Large Hadron Collider can pretty much simulate like a fraction of a second after the Big Bang, like it and with accuracy, like it keeps doing it over and over again. So it's like, not only does our math work, but then when we actually test it by smashing atoms together, it works. Like it is exactly how it's described in physics. So I thought that was really cool. So that was something that I actually didn't know, and that was a big question that I always had growing up. Was like, well, how do we know these things? Like, how is the math so good? But like, yeah, if we can actually test it, that's pretty nuts. But that also kind of presents the problem of why everything past the grain of sand of the universe, like before that, the amount of energy that we would need to test that is literally 1 trillion times more than the current, like the largest collider that we have. So you would basically, it would have to be like some crazy off-world thing that we'd probably all just kill ourselves trying to recreate these conditions.
Yeah, I was going to say something similar. I'm glad you touched on that. Not even touched on it. I'm glad you mentioned that.
Yeah, so that's another issue, is that like in this weird part where physics is all wonky, like what we kind of have to do is, so physics kind of goes out the window, and this is where quantum mechanics and general relativity kind of come into conflict with one another. And I know you know a little bit about that. And like we have some theories that we think could unify them at these moments. String theory, I guess, is one of them. But like there is no real concrete answer. We just know that and that's something else. We don't even know if the universe got smaller than the grain of sand, technically. So that could be a reason why some of those theories in physics don't unify very well, or it could just be that we are missing something really big in either one of them. So, I mean, you know more about string theory than I do. So, what do you have to say on this?
I know next to nothing about string theory.
Oh, really?
Yeah, to be fair. Like, string theory is so... I'm not going to say it's, like, super advanced, but it is just such an abstract school of thought that I can't even understand it. But
really?
So, from the reading that I have done, anything before Planck time, 10 to the minus 43 seconds, to figure out like any more than that, we would have to have like an understanding of quantum gravity, which is something like, I have no idea what that is.
I read that was something that was another issue why those theories don't really like work out together, is because of quantum gravity. But I figured that would be way too fucking complex for me to wrap my tiny monkey brain around. So.
Yeah, I don't know what quantum gravity is. Like if I were to just do a cursory search.
Yeah, what is it? Let's pull it up.
Basically, describing gravity according to the principles of quantum mechanics, where quantum effects can't be ignored, such as when you're close to a black hole or neutron stars. So I'm gonna be completely honest. I don't know how gravity affects quantum mechanics. We didn't touch on that in my classes. But I mean, I guess no. I'm not even gonna hazard a guess here.
I have no earthly idea. So if you don't know, I sure as shit don't. Yeah. So basically, yeah, inflation would kind of most scientists think that it makes so much sense that it probably did happen, but we don't actually have any direct evidence that inflation did take place. So
yeah,
basically all we can say about the beginning of the universe is that the only thing we know for sure is all the way back until it's about the size of a grain of sand. So we don't know anything before that with great certainty. So that opens up the door to a lot of, well, how did the universe begin type thing. And so did you come across anything like any cool theories while you were reading about maybe what happened before the singularity or in the singularity? If you did, go right ahead.
Okay, so some of these are not okay. The one that I'm about to say immediately is not at all supported by science because we have no way to test it.
Yeah.
But I've seen that people have said that the universe was born from like the other side of a black hole.
I have seen that. I was hoping you looked into that more than I did because I spent too much time looking at all the ways we could blow the universe up. So
yeah, unfortunately, there isn't a whole lot that you could look into it because A, we don't know what's in a black hole. B, we don't know if a black hole has an other side, and C, we don't know anything about the very, very, very beginnings of the universe. So at this point, it's just a
complete speculation.
Yes.
Well, everything we're about to say, I think from here on out will probably just be straight up speculation. I wanted to explain a little bit why the Big Bang is correct, the things we know that is correct, but everything kind of after this point is just like, oh, it could happen this way, or it could have began this way. We have no fucking idea. So
now I have in addition to the universe coming on the other side of a black hole, I've read people say that it comes out of a white hole. And that I can say is not true.
Really?
Okay, I mean, with almost certainty, I can say it's not true.
And why do you say that's not true?
Because according to Einstein's equations, to go through a white hole, you need to have a negative mass. Mm-hmm. So to give you an example, imagine that you had a power that only let you push things.
Okay.
So if I had a can in front of me and I use this
I'm going to keep using that can.
Yeah, this can. The can of beer. So I would push this can with positive mass and it would go away from me.
Okay.
But if the can had negative mass, then I would apply this push to the can and it would come towards me.
Ah.
And nothing in the universe exists like that.
Okay. Yeah, I mean, that makes perfect sense. Yeah. I saw a little bit about the white holes, but I don't really know. They're just kind of like, in theory, like we don't even know if they do exist or could exist, but like doesn't Einstein kind of say that like they could, but we have no fucking idea?
Yeah, I mean, like even if they did exist, there's nothing we could do about it to do any testing with them, as far as I'm concerned, because there's no negative mass.
Yeah, I mean,
we couldn't send anything through.
I want to talk more about, the potential beginnings of the universe, but this is where we go into dark territory, and it's like, well, the end is the beginning, which is also the end. So let's go ahead and jump right to some of the endings, so that way we can tie them back together in a nice little bow. So I actually have a little thing I want to preface all of this with, and then you can go or I can go, it doesn't really matter. But for a lot of the scenarios, so based on what we know about physics, math, if we keep running, so just like how we ran our physics backwards and it got us to the Big Bang, if we run it forward, we can also kind of figure out some probable ways that it might die at a certain point in time. So a lot of these are kind of dependent on the idea of dark energy. Matter of fact, it's kind of the driving force of a lot of these. So I kind of went, let me read kind of what I got here. So we know for a fact that the universe is expanding, and for a while we assumed that it would act like most things would. So something that is expanding, eventually it's going to slow down and stop. But when we look out into the universe, we don't see that. We see that it is not only continually expanding, but it's going faster. So it's like throwing a ball up into the air, and it just keeps going faster and never comes back down. Just like quicker and quicker, shoots off into space, like just so.
I've seen that analogy somewhere.
Yeah, I know, right? So we think because of this that there's got to be the existence of dark energy in the universe. And it was first proposed by Einstein, but he actually thought it was a stupid idea and just threw it out. And it wasn't until we discovered that the universe was expanding even quicker than before that we're kind of like, all right, well, something like that has to exist in the universe, because that is the only thing that could explain why the forces keep going. Now, I don't fully understand dark energy, and I'm sure you could probably shed some light on that. I mean, we think it exists. It works out mathematically in a lot of scenarios, but like, I guess, do we even have any direct evidence that it does exist? You explain dark energy, because I don't know shit about it.
Okay, so I admittedly don't know very much.
Okay.
I don't know what branch of physics you have to be in to really get the scoop on dark energy and dark matter. But I don't have the big scoop. I have a slightly more knowledge than the layman might have.
You have a spoon.
I have a baby spoon. So the evidence for dark energy, whatever this thing might be, is it's stronger than gravity's attraction. Like the fact that the universe is expanding is evidence that the gravity in the universe isn't enough to hold it together.
Right.
Like it's an outward, I don't even want to call it push or a pull, but it's something that's causing an outward expansion.
Right. Yeah. So that means that is probably another force that is overtaking gravity. Yeah, I have seen that, and that is, that's a good explanation of it, I guess.
Yeah. I mean, I'm hesitant to call it a force, but whatever it is, it's pervasive. Like it pervades the universe. It's all around.
Okay. Yeah. So because of that, because of the existence of dark energy, if we factor that into a lot of these equations, then the death of the universe is guaranteed in a couple of different scenarios that works out mathematically. So I guess let's start with the big rip.
Cool.
So because that's the one that works out well. So some of these scenarios are more likely than others, and we'll get to that. But so basically, the big rip is an idea of an ending where it says that the expansion of the universe could potentially start moving so quickly that gravity can no longer compensate in holding together like galactic structures. So basically, it gets so fast and it's expanding so much that like star systems start to break apart. And then if it just keeps going, then even fundamental like building blocks of the universe, like atoms, will dissolve and rip apart as well. Basically, because of that, there's kind of like a point where no particle can interact with one another. They just keep getting pulled apart so much. So basically the universe like dissolves.
Well, I think like the big rip is something that interests me just because, I mean, the expansion of space is, I think that's a concept that people may not understand. And I'm going to use the analogy that you mentioned. Like, imagine a balloon that you pull straight out of the box, and you just put, say, uniformly spaced half-inch dots between or all around the balloon in both the lateral, the horizontal and the vertical directions. So when you blow up the balloon, the dots are going to seem further away from each other. And like that itself is pretty interesting. Like if you just imagine the distance between me and this can,
The fucking can.
like the distance between myself and this can could just suddenly grow with the expansion of space, and neither of us would actually move. But the space in between me and the can would expand.
Okay, all right.
And that's why the distance would grow.
Makes sense.
And that is why, at the very end of this big rip scenario, like atoms wouldn't be able to, I mean, even neutrons, protons, electrons, they wouldn't be able to interact with each other because the space in between them, would be just too vast.
Yeah. So basically, and that was kind of the last note that I'd written there, is that it would kind of just like dissolve into like this vast space with a bunch of particles bouncing around that can never interact with one another because the space between them is now so great. So basically, the universe just becomes a giant empty void, like just nothing. So that's pretty crazy.
Now, the heat death ending of the universe is like effectively the same thing.
Yeah, it just on a different scale. I guess one is more like apocalyptic. It's just like, oh, all of a sudden everything is just fucking torn apart, kind of, or just dissolves. And then the other one is more kind of like things just all die out. So yeah, let's go ahead and move on. So this next one is called the heat death, or the big freeze of the universe. The heat death is a little bit of a misnomer, but in physics it makes sense. So the big difference between the big rip and the big freeze is that while the universe is expanding, matter stays intact, but it degrades over a long period of time rather than just being ripped apart suddenly.
So something that you may need to know before going into this is that even stable nuclei can decay. Like things are radioactive because they decay very quickly relative to their stable nuclei. Like I think a proton has a decay time of like several billion or several million years, but the fact is that it can decay.
Okay. So like all matter would at some point decay, right? Like if you give it enough time. So does that mean that even like planets at some point would like break apart, or how does that work?
Yeah, because I mean planets are made of atoms.
Well, right.
And if atoms can decay, then very, 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 very slowly a planet would decay. So it would just turn into energy eventually. Like that's what happens when something decays. Like I believe either like some form of high energy radiation and another particle is released when things decay, and it just depends on the particle that decays what is released.
Okay. Yeah. All right. So that's a good segue. So then, at some point, all of the gases that are necessary to form stars they'll lack the energy that they need to produce them. So no new stars will form at a certain point in the universe, and then all the current existing ones, obviously, as you just said, all matter decays, will decay, explode, like, a whole lot more. I didn't go into any of the neutron star bullshit because that's just, it's too much in one amount of time. But so basically it gets to a point where no new stars can form, and then the existing ones eventually die out, and the universe will go completely dark at a certain point, which is just, kind of terrifying. So then the last entities, after stars and planets and everything eventually decays, the last thing we're going to have in the universe is black holes. Am I correct in saying that?
Yeah. Yes.
Yes.
Because it's tough to make a definitive statement like that, because I imagine black holes are going to last longer than any detectable light. But there will still technically be light, but the black holes should outlast the light if the light crosses the black hole's path.
Yeah.
Tough to say.
Yeah. Okay. Yeah. So from a lot of what I saw, it says that black holes will more than likely be the last things, because it takes trillions of years just for them to lose a fraction of a % of their energy. Like Hawking radiation is apparently incredibly slow. But so we also know that black holes dissolve as well because they emit Hawking radiation. So that does mean they are losing energy, and at some point they will fade out of existence.
Right.
It just takes an unfathomable amount of time for them to dissolve. So, they'll probably be the last things. So, I mean, just imagine this gigantic void of universe where there's just nothing but these fucking holes of death all over that you can't see at all. Like, obviously it wouldn't matter because, like, no one would be alive at that point. But still, I mean, it's just kind of horrifying to think about in its way. So once black holes are gone, the universe is essentially dead. That is kind of its death point. There's nothing that resides in it after that. Just, once again, kind of the same ending point of the Big Rip, just in a different way, that there is just this giant void of nothingness. However, and this was, kind of going back into some of the beginning scenarios, they say that it is possible after an extremely long amount of time that a phenomenon known as quantum tunneling could engage, which could theoretically trigger something similar to the Big Bang or maybe the development of a new universe. Now, I don't know what the fuck quantum tunneling is. I have an idea based on, like, another way that the universe goes out, which is vacuum decay. And I know it's a factor in vacuum decay, but I don't actually know the ins and outs of what the hell quantum tunneling is.
Okay, this is what I was going to explain to you X amount of time ago. So quantum tunneling effectively is when a particle can go through almost like an energy barrier where it normally wouldn't be able to. So imagine you, Trevor, are standing in a living room.
Okay, I'm in a living room.
The door to your bedroom is impenetrable.
Okay, I have no arms. I can't open the door.
Yes, you do not have enough energy to get through the door.
Gotcha.
But you can quantum tunnel through the door and into your bedroom, where you have enough energy to exist.
Okay, but how would I do that? Like,
quantum tunneling.
But how do you what is the idea of quantum tunneling? Like,
so
how does it happen?
In quantum mechanics, there's an equation that governs how particles move. Like, the energy of a particle is governed by the Schrödinger equation.
Oh, okay.
Yes.
Okay.
And I guess to go into a little bit of specifics, the area that you're trying to get into has something called a potential. You can basically consider that the energy. If the energy of the place that you're trying to get into is bigger than the energy that you're trying to go to, if the energy of the place that you're trying to get into is bigger than the energy that you currently have, normally you wouldn't be able to get there. But the math in the Schrödinger equation says that it's possible. There's just a small probability of it happening.
Okay.
So, I mean, that's effectively what quantum tunneling is.
Okay, yeah, sorry.
Like, you move through an area where you don't have enough energy to exist into an area where you do have into a different area
Okay.
where you do have enough energy to exist.
Okay, well, I'm glad you explained that because that concept pops up in the next way that we're going to destroy the universe. So have we ever viewed the existence of quantum tunneling? Have we like witnessed that, or is it just something that is pretty theoretical and like the math is there, but we don't really know if it exists?
Truth be told, I'm not sure about that, but
Okay.
I'm confident that I don't want to say observed it with our own eyes, but that we know it's a thing.
Okay.
Like, I can't cite any examples, but I feel very confident in saying that it's well established and
Okay.
proven to be true.
All right. Well, good enough for me. Yeah. So there we go. Disclaimer: we don't really know, but nonetheless, it is a concept in quantum mechanics. So, okay. So yeah. So let's go on to vacuum decay then, because you explained what quantum tunneling is to me, like the layperson who doesn't understand this shit, and that pops up in here. So what vacuum decay is basically if the universe just decided to delete itself is kind of what it is. So this theory has a lot to do with energy levels in the universe. So, and you'll understand this way more than I am. I'm just giving a general overview here. So everything within the universe tries to move towards its ground state to be stable and to have as little energy as possible. So basically, so let's go to the, and if you've ever seen the Kurzgesagt video on some of this, like you'll kind of understand some of these analogies and a lot of the things that we're saying. Highly recommend looking at them because they explain shit way better and way more visually than we ever could on a podcast, but nonetheless, they're pretty informational. Okay, so let's go to the analogy of like a ball on a hill. So basically, from everything you just described, so a ball on top of a hill has a shitload of potential energy, and the ball naturally wants to roll down into the valley so that it uses all of that energy, and it now rests where it has no potential energy and it's in its ground state. It is the lowest energy possible. It's in the valley of the hill it just rolled from. So anything on top of the hill naturally wants to go to the bottom and just chill there. So basic, like, I mean, even if you go back and look at old textbooks, I remember when you're learning about kinetic and potential energy, that's the analogy that they always use. So here's where shit gets wonky in my brain. All right, so the universe gets a lot of its energy from quantum fields, which, like anything else, also want to have as little energy as possible, which I guess we call this the vacuum state. From all the quantum fields that we know of, they all appear to be in their ground state or pretty damn close to it, but we're uncertain about the Higgs field. So, which apparently the Higgs field we think is responsible for giving all matter its mass. So naturally, I guess that would be something to be concerned about if that's the one that we're not sure if it's in its ground state, its low energy state. So some suggest that the Higgs field appears to be stable, but once again, not really sure. So we'll take that ball analogy again. So we think that the Higgs field could be in what's known as a false vacuum. So it's not in its low energy state. It just looks like it is. So take that ball on a hill analogy. So you roll it down the hill and it's in the valley. But what you don't know is that in the valley, on the other side of the small little hump, there is another gigantic valley for it to go into, but it's just resting in a nice little nook. So this is where quantum tunneling comes in because it can't get over that little hump to go down this other gigantic valley. But if something like quantum tunneling popped in, and just like I can phase through doors, this thing can phase through the other side of this hill, then it still has a shitload of energy left to use for it to hit its ground state, for it to go all the way down into the next valley. So basically the idea of vacuum decay is that if the Higgs field was just to suddenly be like, it drop down into the next valley, that it would release so much energy, like so much unfathomable energy, kind of in like circles of death throughout the universe, that anything it comes into contact with, it would just delete. It's basically just hitting delete on everything. Just you phase out of existence.
Yeah, so like I watched that video and I was like, okay, how the hell does it happen? But as you were talking about it, a connection was made.
Okay.
But I don't know how I'm going to explain it.
Okay.
So the Higgs field is responsible for like giving mass to things, and the Higgs field is the thing that will eventually do the quantum tunneling.
Potentially, yeah.
Yeah, potentially. Okay, so a Higgs boson is just a disturbance in the Higgs field.
Okay.
And imagine the Higgs field as like a 7x7 grid of dots.
Okay.
If in the very middle of the field there were three dots that just coalesced, and the rest of the field was constant, those 3 dots would be considered a Higgs boson. That's a disturbance in the Higgs field.
Okay.
So the Higgs field stretches throughout the universe much like all other fields do. So if at one point in the Higgs field a Higgs boson quantum tunneled, then all of a sudden there would be a large amount of energy in that field. So the other Higgs boson, there would be a lot of energy immediately around the location where the Higgs boson quantum tunneled.
Okay.
So immediately around that mass surge of energy, the Higgs bosons would no longer have to quantum tunnel. They would take the energy from the environment, go up the hill, and then go back down. And then a chain reaction would occur.
That's actually, yeah, they described a little bit of that in the Kurzgesagt thing, like because like once it hits it, you see like a bunch of other ballets like doing the same shit in the background. Yeah. Okay.
Yeah, I didn't understand that until now.
There we go. All right. Well, at least you had an epiphany. We're probably just fucking twisting people's heads into a pretzel on their drive to work. Yeah. So basically, that could cause some kind of chain reaction in the universe, and the universe is basically trying to reset itself on its correct playing field, for lack of a better term. And to do that, it's pretty much got to delete what was currently there. So, I mean, even at this point, like anything it comes in contact with, like it pretty much not only does it just delete the universe, it kind of deletes our idea of physics as well, because then a very basic element of our universe now has a different energy level, which changes a lot of the things that we know in the universe. So this new place is some fucking wacky ass world that we have no concept of. So if this is true, there could actually be, like, the universe is so large that there could actually be a point somewhere or in multiple spots of the universe that this has already happened, and it is just spiraling outward, deleting itself as it goes. And we'd have no way of knowing. But a light at the end of the tunnel of that is that even if that was the case, the universe is so unbelievably large that it could take millions, billions of years for it to delete itself entirely, or just to get to where we are now. So, I mean, it's not like we're just going to suddenly phase out, but, I mean, who knows?
Yeah, I've actually read a research paper on, like, vacuum decay, and I believe the number of years that's expected to happen is like 10 to the power of 139 years. Mm-hmm. And the universe will effectively be dead by 10 to the power of 59 years. So the universe will be dead in a fraction of the time it takes for it to vacuum decay.
Okay, so yeah, it's basically just, yeah. Nonetheless, I mean, we'll all long be gone by then, but just kind of crazy to think about that could be happening out there somewhere in the universe. And then that's also something else, is that, you know, the universe is expanding away from itself, or is expanding quicker and quicker as it goes on, that it might physically be impossible, if it's not traveling at a certain speed, for it to ever reach anything. So it might be happening, it just can't touch anything because the universe is moving so fast.
Yeah.
So yeah, and then that's something else. I don't know if you looked at the final border one. It's kind of like a newer Kurzgesagt.
Oh, like how? I'll let you explain it.
Well, so then I guess you might have seen it. So basically, the universe we know is moving quicker and quicker, that there's actually points that we can never travel to, ever. Like, they are lost to us forever. And that's actually most of what we see in the sky currently. So when we actually look out into the stars, as you know, based on the speed of light and how long it takes light to get here, we're looking at an ancient universe, is what we're looking at. What we're looking at now, I think they say like 90% of it is out of touch for us forever. we could never travel to them if we wanted to, because it's outside of our local group and it's moving away so fast that even if we moved at the speed of light, we would never catch up to it. Which is insane. I didn't know that. I just assumed that like every part of the universe was fair game if we could go fast enough, but I mean, that makes complete sense. It's just crazy to think about that we are literally trapped within our local group. We could never go to anything else. So,
yeah, it's kind of heartbreaking.
Yeah.
Like, imagine if somehow, I don't know how, but somehow we see evidence of life on a star that's, or not a star, but around a star that's just so far away. And there is nothing that we could do to talk to that star or talk to the people around that star. I say people like they're going to be fucking like you and me.
Yeah, no, it is heartbreaking, especially because all the stars we see in the sky, like a fraction of them, there will come a point where we would no longer be able to see them. Because like I think at every given point in a day, there's like several thousands of stars that pass that threshold that we can no longer see them, or that we could never interact with them again, but we'll still see them for a very long time because their light takes so long to get here.
Yeah.
But yeah, still pretty insane to think about. I'm sure we'll talk more about that when we end up discussing like life in the universe, because I think that could probably be an answer to one of the issues of the Fermi paradox. So, yeah, so that was vacuum decay. So then this one, so let's move on to the next one, which this one's my personal favorite because, as Kurzgesagt says, it's kind of the most hopeful in a way, but it still fucking sucks. Like nonetheless, it's still an ending scenario. So, this one's called the Big Crunch, and this one is kind of predicated on the fact that if there is less dark energy than we think, or it decreases over time, then gravity would be able to be the dominating force in the universe. So like right now, like I said, because of dark energy, we look out and we see that the universe is expanding faster and faster. But if at any point gravity decided to take over, then it would finally do what we thought it would do in the first place and slow down and stop. Well, if gravity does become the dominating force at a certain point, it'll no longer expand. It'll start to contract on itself because of the laws of gravity, and it would start coming back the opposite way. So when it does that, basically, it just starts smashing galaxies into galaxies. Everything just gets smaller. It's kind of like it's going back to a big bang state. Basically, the universe is contracting on itself eventually. And then this is crazy. So because of that, the universe was kind of hotter and denser as it got smaller. Well, it eventually gets so hot in the universe that it fucking cooks stars from the inside out.
I think you're talking about the outside in.
Was it the outside in? Oh,
Yeah.
I thought it was the inside out. Wait, I don't know. Nonetheless, it fucking like bakes stars.
The temperature outside the stars would be greater than the temperature inside the stars.
Yes.
Eventually.
Yes, there we go. Yes. And so I thought that was fucking nuts. I was like, holy shit. And then so at a certain point, all black holes merge with one another. So basically we already have supermassive. So it would be called like a mega fucking massive black hole. And they just start swallowing it swallows everything, including itself, which how does that even work?
I have no idea.
Okay, well, there we go. So it swallows everything, including itself. And at this point, it could cause kind of like an implosion. And because of that, it could set off another Big Bang. It could be, it could create the circumstances of the singularity or something incredibly similar to it, which once again, at that point in time equals 0, we don't know what happens within the singularity or how it got to that point. So essentially, yeah, it could be basically the universe starts with a Big Bang, it expands out, and then it comes back, contracts on itself, and then boom, causes another Big Bang. And it's literally that trickles into an idea that is offshoot of this, which is the Big Bounce, where basically the universe is just bouncing. It's constantly destroying and recreating itself, like in this endless cycle. Now, does that mean it's like, oh, everything just gets like repeated or it's the same universe? Like, no, it could literally be creating different universes with different laws of physics each time, but nonetheless, just constantly creating and recreating itself. That's my favorite one because I like it a lot. And also, once again, it makes me think of Dark. So, yeah. So what do you think about this one? Do you have any notes on it?
I definitely think it's an interesting idea. Don't have very many notes just because a lot of it is outside of what science can touch. Like, I mean, as of right now, I don't think it's as supported as the Big Rip, just because, I mean, one, we don't know how dark energy behaves, so we don't know if it decreases in strength over time.
Right.
But if it does, I mean, that is kind of a, I don't want to say light at the end of the tunnel because we're going to be dead anyway, but
Well, right, but nonetheless,
it's like a positive light or a positive end of the universe, like death, rebirth type shit.
yeah, exactly. The beginning is the ending, and the ending is the beginning. Because even if we, we never get to experience it, nonetheless, it's like, hey, at least there is a chance that like everything that is ever known ever doesn't just completely go dead, and that's the end of any concept of anything. It's like, nah, like at least this one, it could spark something new.
Yeah.
And, it's not all for naught. There is something else out there. There is some other form of existence. But based on everything that we know, that we currently know about dark energy, it's looking like heat death is definitely the most likely. That at a certain point, things just keep expanding. Stars can't form. Everything goes black. Everything decays over time because the universe is essentially infinite. And that's it. It just fades out into another void.
As dark as this might sound, humanity will likely be long gone before any of this happens. Nobody's going to have to suffer through this.
Oh, no, yeah. These are all, like, terrifying concepts that no one will be able to experience because, like, any kind of living organism would be gone by then. I mean, the second your star's fucked, you're fucked, pretty much. Unless, you travel to other solar systems, but we're not anywhere remotely close to doing that. I mean, at the rate that we're going, like, we'll be stuck in our solar system for a fucking while until we can figure something out that we would have to travel at the speed of light to be able to get out of our solar system and go to another, or we'd have to travel faster.
Eventually.
Yeah.
Like, this is the time scale between when this is going to happen and where we are now is like saying the difference between a single day and like 1,000 lifetimes of the entire universe.
Yeah.
Like, it's such an insane time scale difference that it's not going to matter where we are because we'll probably be gone.
Yeah, I don't even think there is like a problem. Like, I think, well, yeah, I mean, we just will be because if all matter decay, there'll just come a point where it's just impossible for anything to sustain itself. Everything will just be gone.
Well, sorry, I mean gone before we have to deal with any of this stuff.
Right, yeah, exactly.
And I say probably because I don't know that for sure, but I'm assuming.
Yeah. I mean, like I said, at the rate we're going, like our sun will just kill us. So,
Oh, yep, you're right.
Yeah.
You're correct. But we could move to Mars or...
Would Mars work? Wouldn't it kill us if we were on Mars too?
Yeah, sorry, it'll swallow the 4 inner planets, Mercury, Venus.
Earth and Mars.
Yeah.
Yeah.
We'll figure something out, I'm sure. Unless we all just...
Well, I mean, we got like what, billions of years before that happens anyway. So we have billions of years to figure out how to get out of our solar system or move to a planet that won't be fucking cooked when the sun expands.
We have 4.5 billion years to figure that out.
There we go. Yeah, hopefully we can cook up something by then. Yeah, so then there's some other, I don't know if you looked into any other beginning or endings. Did you look into some of the wackier ones?
I've looked at an idea, like one that really stuck out to me. It actually isn't a beginning or an end. It's called the plasma universe theory.
Okay.
And I'm not sure if it's a theory in the scientific definition, but it may be a theory in the layman definition.
Okay.
So to give you some background on this, 99% of our universe is plasma.
Okay.
Galaxies, stars, 99% of all that is effectively stars, and stars are made of plasma.
Okay.
So plasma is an ionized gas which conducts electricity, and if you don't know what ionized means, it's basically just composed of atoms that have either lost or gained an electron.
Okay.
Or a few. So ionized means it's just differently charged than the neutral state of the element. So the plasma universe states that the entire universe is governed by electric currents and enormous magnetic fields.
Okay.
And I think that's insane because the strength of a magnetic field decreases by the distance you are away from it squared. So magnetic fields get really weak really quickly, just like electric fields. So for our entire universe to be governed by a magnetic field, like, that would require a shit ton, and I mean a shit ton of, like, electric energy throughout the universe.
Oh, so so this isn't something you thought was like cool. You thought this was something that was really dumb because it can't work, kind of thing, or?
No, it was an interesting idea. Now, I probably should have said this before. This is not supported by any astronomical observations.
Okay, there we go.
Or many astronomical observations. The fact that 99% of the universe is plasma, that's true. But aside from that, the astronomical evidence is pretty slim. All the evidence that supports the plasma universe idea is, like, just stemming from a few lab experiments. And I say few, it's probably a lot more than a few. But lab experiments support the plasma universe idea more than anything else. Not actual direct universal observations.
Makes sense. Yeah. So I think the only wacky one that I don't even know much about it, but still that it's always fun to think about is then there's obviously simulation theory.
Yep.
That nothing that we see is real. This is not the base reality, which could make sense for why physics gets all wonky and it's just thrown out the fucking window when you get too far back, because then it's just when the simulation switched on, or that's like just they put it there to fuck with us in the simulation so we wouldn't think too much about it or some shit. But I don't know. Simulation theory is always one that's like cool to me because like when you think about the idea, it's like, oh well, yeah, it's like we're getting smart enough to create virtual worlds that are kind of realistic, and then if we imagine thousands of years from now, if technology keeps on the same path, we could basically create a world that is indistinguishable from our own, like almost identical in every way. And it's like, okay, well, keep expanding that time, and then it's like, all right, what if someone decides to flip on a simulation, and then that simulation makes a simulation, and then that simulation gets so smart it makes a simulation. So like I always thought that was really cool to think about, but I mean there's literally, I don't think there's any basis in reality of that. It's just like one of those, it could be, could not be, like flip a coin. It's like 50-50.
Yeah, the only reason, like I saw that too, the only reason I didn't like put that down in my notes is because like there is there is effectively no basis in science to support it.
Yeah, I haven't seen
But
anything.
it's very cool to think about.
Yeah, I think I've seen an article that like scientists did kind of like discover something, and they were like, computing power would never be able to mimic this in the universe or something like that. And then it's like, well, I mean, what if it was just like the craziest fucking computer you'd ever seen? Like, it's like, so.
I mean, it very well could be.
Yeah, but this is also kind of like a lot of this logic is the same logic as like the flying spaghetti monster type shit. Like, it's like, well, you can't prove that it doesn't exist, therefore it could. So yeah. Just fun to think about, but I didn't write down any notes on it because I'm just like, nah, it's not gonna give any credit to it. All right, well, guys, thanks for tuning in to season 1, episode 2 of the Modern Goonies podcast. I've been your host, Trevor King Minor, and this has been my lovely co-host, Michael Ross.
It's your boy, Michael fucking Ross.
And join us next week for season 1, episode 3. Much lighter material on this one. We're not gonna blow your brains, so stick around. See you then. Good night, everyone.
Good night.